For a moment in the 1940s, engineers promised a future where bombers would fly farther and faster, freed from tails and a conventional fuselage, thanks to the radical flying wing. The promise was simple and audacious. Records showed a 10 to 20% leap in aerodynamic efficiency, with the Northrop N-1M taking flight in 1940, and the Horton Ho 229 appearing in 1945. Yet that vision vanished, quietly and completely. What made aviation's most daring shape look unstoppable? And what secret flaw led to its disappearance? On paper, the flying wing offered a promise that was difficult to ignore. Engineers calculated that by removing the fuselage and tail, the aircraft's entire surface could be devoted to lift. Every square meter of the wing contributed, with no drag wasted on supporting structures. This single-minded pursuit of efficiency translated into numbers that caught the attention of military planners and designers alike. The lift-to-drag ratio, the measure of how much lift an aircraft can generate for a given amount of drag, stood at the heart of the argument. For the flying wing, that figure improved by a full 10 to 20% over conventional bombers of the era. A 10% gain in lift-to-drag did not simply mean a sleeker silhouette. It meant the possibility of flying farther on the same amount of fuel, or carrying heavier payloads to distant targets. In the world of strategic bombing, where every extra mile of range could mean the difference between reaching a target or falling short, such an improvement was not a footnote. It was the headline. The calculations were clear. A bomber built as a flying wing could, in theory, cross oceans while burning less fuel, or deliver a greater load without sacrificing range. This was not just theoretical. Wind tunnel tests by Dr. Theodore von Karman and others confirmed that the flying wing's reduced wetted area and elimination of interference drag produced real, measurable gains. The numbers became a kind of incantation for advocates. 10 to 20% more efficiency, a leap forward at a time when incremental advances were the norm. The allure was mathematical, almost pure, a rare moment when the future seemed to hinge on a single, quantifiable promise. Workshops that once built wooden gliders now echoed with the whine of engines and the scent of fresh-cut aluminum. In 1940, at a dusty, dry lake bed in California, the Northrop N-1M lifted into the air for the first time. Its wingspan stretched just over 38 feet, but it carried the weight of an idea that was both radical and stubbornly persistent. Test flights followed, more than 200 in total, each one a careful negotiation between theory and the unpredictable language of wind. Jack Northrop and his team watched as their creation bucked and twisted, revealing both the promise and the difficulty of controlling a plane without a tail. The N-1M's compact frame and twin pusher propellers made it look more like a child's sketch than a weapon of war. Yet every minute aloft translated mathematics into physical reality. Across the Atlantic, the closing months of World War II brought a different kind of revelation. In April 1945, American troops advancing through Germany seized a strange, unfinished aircraft at a Gotha factory. The Horton Ho 229, with its 20-meter wingspan and twin jet engines, was unlike anything in the Allied inventory. Its wooden skin concealed a blend of ambition and desperation, a last gamble by designers Reimar and Walter Horton to deliver a 1,000-kilogram payload, 1,000 kilometers at jet speeds. The prototype V-3 was incomplete, but its existence was enough to draw the attention of intelligence officers and engineers alike. Crated and shipped to the United States, the Ho 229 became both a trophy and a puzzle, its stealthy silhouette hinting at possibilities decades ahead of its time. In these moments, the flying wing crossed a threshold. No longer just a set of equations or wind tunnel models, it became a physical artifact, tested in the open air, captured on the battlefield, and scrutinized in secret workshops. The question was no longer whether the flying wing could exist, but whether it could be made to work. The numbers themselves carry a certain gravity. The Horton Ho 229, recovered from a German factory in 1945, spanned 20.03 meters from tip to tip, just over 65 feet. Its twin junkers, Jumo 004 turbojets, produced a combined thrust of nearly 17.6 kilonewtons, enough to push the wooden airframe toward an estimated top speed close to 977 kilometers per hour. Empty, the Ho 229 weighed about 4,600 kilograms, yet it was built to haul a 1,000-kilogram bomb load over 1,000 kilometers. These were not the ambitions of a drawing board. They were cut, glued, and riveted into shape. The American response arrived in the form of the Northrop YB-35 and its jet-powered sibling, the YB-49. Both shared a wingspan of 52.4 meters, 172 feet, dwarfing the Ho 229 by more than 30 meters. The YB-35 relied on 8 radial engines driving contra-rotating propellers, a solution that proved as complex as it was ambitious. Its empty weight approached 80 metric tons, with a maximum takeoff weight nearing 180,000 kilograms. The YB-49, shed of propellers and fitted with 8 Allison J-35 turbojets, tipped the scales even higher, 86,000 kilograms empty, nearly 192,000 kilograms at full load. In level flight, the YB-49 could cruise at 670 kilometers per hour, with test pilots pushing it to almost 800 kilometers per hour. These figures were more than engineering bravado. They defined the physical boundaries of the flying wing dream. Each measurement, a promise to fly faster, carry more, or outlast the bombers of the day. But for every meter of span and every kilonewton of thrust, there lingered the question of what those numbers could not reveal. Even as the flying wing's dimensions grew more impressive, its stability margins shrank to the edge of impossibility. The center of gravity and the center of pressure, two invisible points that decide whether an aircraft flies straight or tumbles, were separated by less than 30 centimeters. On the ground, this gap looked trivial. In flight, it meant that a shift as small as a fuel load or a gust of wind could tip the balance from control to chaos. Engineers tried to compensate with elevons, control surfaces that blended the roles of aileron and elevator, but their authority was limited. At high speeds, the forces on these controls spiked beyond what the hydraulic servos could handle. Mechanical linkages relying on cable tension and hydraulic pressure responded in tenths of a second. Latencies measured from 0.1 to 0.5 seconds. In those fractions of a second, the wing could begin to yaw or pitch, and the correction would arrive too late. Oscillations set in, with frequencies between 0.5 and 2 hertz, while the control systems could only reliably damp movements up to 1 or 3 hertz. The result was a mismatch. Disturbances appeared faster than the aircraft could react. Test pilots described a hunting motion in yaw, a subtle but relentless wandering from side to side. Each attempt to correct induced a new wave, never quite settling. The numbers that once promised efficiency now revealed the limits of physics and machinery. For all their ingenuity, the engineers could not outpace the laws that governed flight. The margin for error was measured in centimeters, and the time to react in fractions of a second, too narrow and too slow for a world that demanded certainty. On June 5, 1948, the Northrop YB-49 lifted off from Muroc Air Force Base, one of only 2 prototypes ever built. The crew included Major Daniel Forbes and Captain Glenn Edwards, both seasoned test pilots. The bomber climbed into the clear desert sky, its 172-foot wingspan casting an improbable shadow over the runway. At altitude, the aircraft began a series of maneuvers. Telemetry recorded subtle oscillations, movements that had troubled engineers for months. Then, without warning, the wing structure failed. The YB-49 broke apart in mid-flight. Wreckage scattered across the Mojave, leaving no survivors. The official accident board cited structural failure aggravated by instability, echoing concerns raised in earlier test reports. The loss of half the experimental fleet in a single morning brought testing to a halt. Silent hangars and grounded prototypes replaced the optimism that once filled Northrop's workshops. In the aftermath, investigators pored over control logs and debris, their conclusions heavy with finality. The dream of the flying wing was no longer just threatened. It had suffered a mortal wound. In 1949, the United States Air Force convened its procurement panels, pencils poised over ledgers that had grown thin in the post-war years. The numbers for the flying wing were stark. Development costs for the YB-35 and YB-49 had climbed past $20 million, with no production orders in sight. Congressional hearings echoed with questions about risk and return, and budget charts projected a future where every experimental program carried a price measured in lost squadrons and canceled contracts. Against the flying wing, the Convair B-36 Peacemaker stood as a known quantity. Its conventional shape and proven, if lumbering, performance matched the strategic doctrines of the day. The B-36, at $3 to $4 million per unit, promised reliability at scale, while the flying wing's projected production costs remained an open wound. On paper, the B-36 could deliver a heavier payload over greater distances, and its assembly lines were already humming. Faced with fiscal pressure and a doctrine that favored certainty over ambition, the Air Force issued its verdict. The flying wing would go no further. Contracts were terminated, prototypes scrapped, and Northrop's workshops fell silent. The ambition that once soared above the Mojave was reduced to a line item, erased by budget and bureaucracy. Today, the flying wing survives only as radar evading shadows. Its promise realized in the B-2, with a 172-foot wingspan, yet its ambition remains unmet for everyday flight. Progress often means letting go of beautiful ideas, but each lost dream leaves a question. What if the future we abandoned was the one we needed most?